In this video, I'm going to be talking about the universal law of gravitation. So it can be written that the force of gravity is equal to this gravitational constant times the mass of the larger body times the mass of the smaller body, all divided by the radius squared, and it'd be negative. And another way you can read this is that the force of gravity is directly proportional to the product of the masses and is inversely proportional to the radius squared. So this equation is negative because the force of gravity is downwards towards the surface of the planet, or towards the center of the planet. The radius is just the distance between the center of masses. So as I've said, the force is calculating a force between two bodies and of one body on the other. It's only one force per equation. So let's say the radius is the distance from here to here. It's the force of gravity acting on this object at this radius, diluted at this radius, towards the center of this object. And the radius is the distance between the center of masses. Newton didn't know what G was, but he did assume that if you was to have the mass of the planet double, that the force of gravity would double. So that means they're directly proportional. That if you double the mass, the force of gravity doubles, and that ratio is equal to a constant. Same thing if you double the mass of the smaller body. You have to double the force of gravity also, and it'll be equal to a constant, that ratio. And that's common sense. I mean, you double the mass, you double the amount of stuff you have. If you have some gravitational force as a result of the amount of matter you have, the amount of mass you have, if you double that mass, then you would double the gravitational force. Now, I'm going to talk a little bit about how the force of gravity is inversely proportional to the square of the radius. Newton believed that the gravitational formula should be written over r squared because of the inverse square law. A good example of the inverse square law is this square law right here. So essentially, at one radii, the surface area of a sphere at 1 radii is some 4 pi r squared. And that at double the radius, that 4 pi r squared becomes quadrupled. So 1 square meter in the 1 radii is going to quadruple at 2 radii. So essentially, whatever is in that 1 square meter at 1 radii gets distributed over a 4 times greater area at 2 radii. Newton believed that the force of gravity was inversely proportional to the square of the radius. So what that means is, at some radius, gravity would have some force. And at double that radius, you double that 2, double that r, you get a gravitational force that's 4 times smaller . You get a gravitational force that's 4 times smaller as the radius doubles. Another thing about gravity, the gravitational force between two bodies are equal. So the gravitational force calculates the force between two bodies of one acting on the other, and not both of them acting on each other. But those forces are equal. So I'm going to prove that. So let's say here's a 2 kilogram object and here's a 3 kilogram object. This 1 kilogram, one individual kilogram, is going to pull on this kilogram, and this kilogram. They're pulling on each other. we're just pulling on each one of these with some force. And the same thing for this one, and this one. So that's 2 times 3. It's the force between them is just 2 times 3, you can say, without any units. And similarly, this kilogram in this object is pulling on this one and this one. This one's pulling on this one and this one, and this one's pulling on this one and this one. So that's also just 3 times 2. So it's the same force acting on each body. It's a little counterintuitive, but this is the proof that the moon pulls on the Earth with the same force that the Earth pulls on the moon. Each kilogram of the moon pulls on each kilogram of the sun. Like each individual kilogram of the moon pulls on every kilogram of the sun, and each individual kilogram of the Earth or the sun pulls on the whole kilogram of the moon. For Newton to prove that gravitational force decreases by the square of the radius, he must first have gravitational force written in this form, where these masses cancel and acceleration due to gravity at 1 Earth radii is gm over r squared. Now, at 60 Earth radii away from the center of the Earth, acceleration due to gravity should be 3,600 times stronger than the acceleration due to gravity near the surface of the Earth, which is this. I'm sorry, I meant to say that the acceleration due to gravity at 60 Earth radii away from the center of the Earth would be 3,600 times smaller than the surface gravity of the surface acceleration due to gravity at 1 Earth radii, which is this. So we can compare the acceleration, the centripetal acceleration of the moon, which is about 60 Earth radii away from the center of the Earth, to the surface acceleration due to gravity, and it should be 3,600 times smaller at the surface at the centripetal acceleration of the moon. So Newton can calculate the acceleration due to gravity near the surface of the Earth by this formula right here. Let me write it down. So you can drop an object with initial velocity equal to 0 and time it for 1 second of free fall. And if you assume the acceleration due to gravity is constant, you'll find that after 1 second, it'll drop about 5 meters. And given that, you can solve for acceleration due to gravity and find that it's about 10 meters per second squared. Negative, because this is negative. And the centripetal acceleration of the moon is just v squared r. Aristarchus knew that the distance to the moon was about 60 times Earth's radii away from the center of the Earth. We knew the velocity of the moon around the Earth, so we can calculate that. And it turns out that the centripetal acceleration of the moon is about 3,600 times smaller than the surface gravity of the Earth, therefore proving Newton's idea that gravitational force decreases by the square of the radius. Newton knew that this equation took this form, but he didn't know what this capital G would be. He knew that it's the gravitational force of the force, so it should be mass times acceleration, and the units must be newtons. Standard Newton must be newtons, and that in the form of mm over r squared. That's just kilograms over meters squared. It's not the unit of newtons. So there must be some extra terms that must be there that are hidden, that you must discover through experiment, that Isaac Newton didn't know how to actually solve for this constant right here, the gravitational constant, but a guy named Henry Cavendish did. Cavendish and the Cavendish experiment used a torsion balance to derive the gravitational force between, let's say, a small ball on a torsion balance, on a torsion rod, on either end of the torsion rod, and two larger balls nearby. And it was all on this torsion rod hanging by a thin wire, allowing it to twist. And there's a small gravitational force between the balls that would allow it to have a small acceleration or angular acceleration. Small torque would be applied. And believe it or not, you can actually calculate that gravitational force without knowing G right here. Cavendish figured out a way where you can do that. So he figured out that gravitational force, plugged in the masses of the balls and this radius between their center of masses, and solved for G. Henry Cavendish measured the gravitational constant to be about 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. With this constant actually figured out, you can actually figure out the mass of the Earth. Because here's the equation for Newton's gravity. You can equate it to the weight of an object and plug in the mass of the object, the gravitational force, and the radius between them, and then do some rearranging to solve for the mass of the Earth. And the radius of the Earth was figured out by Eratosthenes. And this is very important because now that we can know the distance to the sun by method of Aristarchus, so we can figure out the mass of the sun. We can figure that out by plugging the mass of the Earth. Let's say the centripetal acceleration. We can figure out the centripetal acceleration of the Earth is v squared r, and then the centripetal force is the gravitational force. So that's going to be the mass of the Earth times v squared r. And that's the gravitational force. So you can equate that to gmmr squared, and you can plug in the mass of the Earth, the radius between the Earth's center of mass and the Sun's center of mass, and you can solve for the mass of the Sun. So we can do this with all the planets and the moon, and we can figure out that basically with the configuration of the mass of the Sun, the mass of the planets, the distance between the suns and the planets and the moon, and all these distances, that a Copernican model or a Ptolemaic model has to be what's going on in reality. So, like, let's say there might be a tectonic system. We can know with the phases of Venus that the Earth, that the planets orbit the Sun. In the tectonic system, it could be a little bit different, where the planet, I'm trying to remember how the tectonic system is. It's where the planets, the Sun orbits the Earth, and the planets orbit the Sun. So the phases of Venus shows that Venus and Mercury orbit the Sun, which means that we would probably orbit the Sun. And the gravitational law disproves the tectonic system, because with the mass of the Sun is such a way it is, the distance between the Earth and the Sun, the gravitational force between the Earth must be great enough to where the Earth orbits the sun. That's just how it is. And now the moon must orbit the Earth, and the planets must orbit the sun. And it's not a tectonic system. So that tectonic system is ruled out by the gravitational force and Cavendish's derivation of G. And the geocentric model is definitely ruled out. The Ptolemaic, I was saying the Ptolemaic, I meant the Copernican model earlier. The Copernican model and Copernican model is the most certain models by gravitational formula that Newton came up with, and Henry Cavendish's constant, and other Aristarchus and Eratosthenes distance methods. We can figure out that we are not in a tectonic system, we're not in a Ptolemaic system, but we are in a Keplerian Copernican model. And this stuff helps you really learn about reality, gives you insight into what's really going on. And yeah, I could talk later into more about how we know that it's not a Ptolemaic model. I mean, because Kepler came around and we discovered that we can actually discover the periods of the planets and show that epicycles is just an apparent retrograde motion of the planets due to Kepler's third law. It's just the way it is. But other than that, that's Newton's universal law of gravitation.